Hello everyone, and welcome to the first video lesson of this math course. I'm really looking forward to teaching college algebra and trigonometry all in one video series on its own. Um, of course, bear in mind that I will also be learning this math, and the purpose of these videos is to reteach what I have learned so far in these topics so that you can also gain an understanding. But not only that, but I can also get a better understanding of what I'm doing. So, without further ado, we are first going to do 1.1 real numbers, and these are the algebra essentials, because a lot of the equations you can't really do without really understanding this stuff. So, this is the beginning, I believe, when it comes to learning math at a college level. So, right. So we got at least five things we're gonna do for this video. We have the objectives. Classify a real number as a natural, whole, integer, rational, or irrational number. Perform calculations using order of operations. Use the following properties of real numbers: commutative, associative, distributive, inverse, and identity. And then we have evaluate algebraic expressions, and then we have simplify algebraic expressions. As we go through each one of these, I'll be checking each one to let you know that at this point we have basically learned how to do each of these objectives. Um, but let's get started. Okay, so I'll be removing that. Okay, so classifying a real number. So think of it as numbers we use for counting or like numbering items. So what natural numbers are going to be, so natural numbers, they are going to be numbers like 1, uh, crap, whoops. So basically 1, 2, 3, 4, 5, etc. And we basically it's goes all the way to infinity, like just regular numbers. And natural numbers will be basically the same as counting numbers. However, when we go into whole numbers, so whole numbers will always include the zero at the beginning, and we do not start at one. So it'll be like 0, 1, 2, 3, 4, and 5, and like going to infinity. So that's whole numbers. When we go into integers, that is a completely different story. Now that we go into integers, it's not only using, like, it'll be using basically whole numbers, but with integers, not only are you going counting up, like 1, 2, 3, 4, 5, you're also going into the negatives. -1, -2, -3, etc. So now we have rational numbers. Rational numbers are written differently. For example, think of like fractions, where here, what's the best way to describe it? So think of a fraction. I'm going to use variables n over n. So basically, m and n would be integers, except n would not equal 0, because anything divided by 0 just gives an error. A computer cannot process it. So this would be a rational number. Now, before we head into continuing onward from here, like let's try and do some examples where we utilize natural numbers, whole numbers, integers, and rationals. Like how do we tell the difference? So I'm going to clear this. And all right, so let's give some examples like 7, 0, and then 8. So for this, um, write each of the following as a rational. We're going to write each one as a rational. And this should be easy enough. We know a number cannot be divided by 0. Just know that. But since these are whole numbers, all we have to do is put them over 1. Now this would be considered a rational number because it's written as a fraction, but it's also over 1 to maintain that 7 is a whole number. Once you simplify it, of course. The next one, 0, you still put it over 1, and it'll be still 0 because 0 divided by 1, 0. 7, same thing with 7. Like it's 7 divided by 1, it'll be 7. And we should probably already figure out what 8 is already going to be, which is going to be 8 divided by 1. And so if this were negative, the same concept applies. It would still be divided by 1. There is no difference at all. So those are rational numbers. Now, let's continue. Um, all right. So, another thing with rational numbers that I'd like to touch on, um, although it's fractions, we can also express it in a decimal form. So, usually there's two different kinds of rational numbers and like two kinds of decimal forms that we need to be aware of when it comes to rational numbers. So rational numbers can also be there, you'd have a terminating decimal. Just writing this down. And you have a repeating decimal. So a terminating decimal, for example, if we take the fraction like 15 over 8, this would convert to like 1.875. And this is a terminating decimal because it does not go on for like an infinite amount of time. Like it doesn't repeat constantly. And what I mean by that is we take a rational number like 4 over 11 and we try dividing this. The decimal we get will stretch on forever. And I mean forever. Like it won't stop. Like it'll just, if you were to do like, if you were to calculate in division using handwriting, even or a calculator, you'll see that it'll just be the same number over and over again until the very end. This is a repeating decimal. Like we use this line above it to basically tell that it will be repeating forever. So now that we did that, whoop, now that we did that, what we want to do is try a few examples and tell whether it is terminating or a repeating decimal. So let's clear all this. All right. So let's get some example equations. So we'll do negative 5 over 7, 15 over 5, and then let's do 13 over 25. All right. So negative 5 over 7, which if we calculate that, it will be, so let's do, I should probably set this up differently. I realize it wouldn't work if I were to set it like this. Okay, so what was it? Like 15 over 5, 15 over 5, and then 13. Whoa, I do not know how to write today. Okay, 13 over 25. Wow, oh my God. Oh man, the quirks of teaching. Okay, here we go. So, if we were to calculate negative 7 over 5, we would get something like negative 0.714285714, and we can already tell it's already starting to repeat. So it is most likely going to be 285 that we see. This would be a repeating decimal. So this would be repeating. Now, if we do 15 divided by 5 for this one, we'd only get 3 because it's simplified to 3. It is not extending. However, if we did convert it into a decimal form, all we would have to do is add a point 0, and it would still be a whole number. It's just there's nothing after it to really say anything. So this would be considered terminating. Now we have 13 over 25. Now, if we were to calculate that, we would be getting 0.52. And this is fairly straightforward. We don't see it continuing on for a very long string, so this is also a terminating decimal. And it's pretty simple enough. So just know that if a decimal repeats, it is repeating. If a decimal stops at one point, it is a terminating decimal. That sounds easy enough. All right, let's clear this out of the way. All right, now we're going to deal with irrational numbers. Now, this one, well, as you would probably guess, is the opposite of regular rational numbers. Um, so I want to take some time with this one. So irrational numbers. So basically, we will encounter numbers in certain points where you cannot really give like a regular rational, like it can't be rational at all. Like you can't simplify it, you can't change it to make any sense. Like this will be a number where it will look like you can't do anything else with it, because if you do, there's a good chance it'll be wrong. And so, um, basically, uh, where the number that's shown here, where you have like h is not rational. It's pretty hard to express this, but um, we'll keep that in mind. So we're going to try some examples to kind of really start showing what I mean by this. So we're going to do some practice problems with this one. So we'll have square root of 25. Then we will have 33 over 9. Then we'll have square root of 11. Then 17 over 34. And then we'll have a repeating decimal. I, I, well, this, it, it is technically repeating, but I wouldn't really say it, and there will be something. So like, let's take 0.3033, 0.333, and you kind of get the gist of it. All right. So, square root of 25. Like, it's simple enough. It will be 5. Because 5 times 5, 25. So, it is a rational number. So, it'll equal 5. It is rational. Just to give a frame of reference. And, okay. 33 over 9. It's a fraction, of course. 33 divided by 9. In order, we should simplify this even more to really get a better understanding of what we're dealing with. So we multiply the top and the bottom because they can be divided and simplified into a smaller fraction, and you make it easier to deal with. So we multiply the top by 11 and the bottom by 3. Or, I mean, not multiply, what am I saying? I mean divide. Whoops, whoops. Because if I multiplied it, it just would make everything a lot harder. So I mean divide. So division. Then we'd have 11 over 3. And when we try putting that into a decimal form, we would get 3.6 repeating. Like this will keep going on for a while. And this would still be considered a rational number like before, because it is still something that we can like determine as a rational number. It's like nothing odd. Now, this is where things get different. Square root of 11. Now, we already know that the 11th square root would probably equal some crazy decimal in the calculator. However, this is what I mean. It cannot be simplified any further. It is basically stuck as the square root of 11. You cannot change it or anything, or you can't really calculate it into some way. Therefore, it is a irrational number when it is stuck like this. Like, you cannot simplify it any further. And this is what I mean by irrational numbers. Like if we go here, like multiple or divide this by like 17, for example, and divide this by 2, or divide, wait, no, 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 no. We divide all this also by 17. This would equal half, which in decimal form is just 0.5. It is terminating. It is rational. Now, once we get to this decimal down here, now this is where we start to think a bit deeply because we see it is a repeating decimal. It is non-terminating. However, because each of the, like, as we can see, the sets of threes increase every time. So we do not know also if there will be an end to the sets. It'll probably just increase, keep increasing to like infinity. I do not know. So we can't really tell whether it is a terminating or a repeating decimal because of the way the pattern works. And therefore, this number is also not rational. It would be considered an irrational number because we can't clearly see if it will be terminating or not. So yeah, this would be the breakdown for irrational numbers. And I'm sorry if it seems a bit weird, but trust me, I'm doing my best here. All right, so let's get this cleared. Let's get this cleared. Oop, there we go. All right, so let's just take a break for a moment because it's probably a lot. So, real numbers. There we go. So, real numbers, we now know, can either be rational or irrational. Can't be both, however. But the sets when we deal with rational and irrational numbers, when we put them together, we make up a set of real numbers. So it's kind of the same as when we were talking about integers before, except we can divide the real numbers like as well into three subsets, like negative real numbers, zero, and positive real numbers. So, um, let's take a number line, for example. Um, wow, I cannot draw a straight line. Um, let's just change this. But let's take a number line to make this easier on ourselves. So when we think of a number line, center, we'll have it set to 0. And we will have positive leaning to the right and negatives to the left. Sorry if it's not even, but this is just kind of to emphasize what I mean. So we have 0 in the center and basically a fixed unit distance would mark each integer, like with each tick right here. And the one thing to know is that each point on the number line corresponds to exactly one real number. And this would be considered a one-to-one correspondence. So, like, this would be a real number line. Like, it is basically the same as integers, but you will understand what I mean soon enough. But yeah, this would be the real number line, real numbers. So just remember this part. It'll make it all the easier. All right, let's clear this again. So let's do some more practice problems. And this time we're going to classify each number as either positive or negative and as either rational or irrational. And does it lie left to the number line or the right? Or should I say like left of 0 or right of 0? That I'm pretty sure what I said before made no sense, but let's keep going. So we will have some practice problems. Let's see, let's do negative 10 over 3. And let's do square root of 5. Let's do a negative square root. Ooh, that will be fun. Negative 2, the square root of negative 289. Let's try negative 6 pi. Pi is a very interesting one. And then let's try a decimal. So let's do 0.615384615 3, 8, 4. So we already know this is repeating. Like it's a dead giveaway. We know it's repeating. All right, let me get some water here. Yeah, better. Okay, so negative 10 over 3. We consider this as a negative number, and it is a rational number. So it is negative, rational, and we'd put this on the left of the 0. Simple enough. So now we have the next one, square root of 5. It is already irrational because we cannot simplify this any further. I did not go into depth before in simplifying the previous problem because all we're doing is telling whether it is positive or negative and the position on the number line. So this would be positive. However, it is irrational and it would lie to the right of 0. All right. Next, we go to the negative square root of 289. So I kind of want to make this simple and say that let's keep the negative separate for now and take the square root of 289. So the negative would be separate for now, its own. We'll take the square root of that. It would be 17 squared. Each one of these would cancel out, and we multiply the negative back, and we'd have negative 17. So it is negative. It is still a rational number, so it would be, oh, I almost wrote positive. All right, so it is still negative. It is rational because we were able to simplify the square root to its simplest form. And it will lie to the left of 0. All right, 6 pi. We do not need to simplify this any further. Because we know what pi equals to, very large decimal, I will not write down every number on that. But like we know it goes on for a while and it is terminating at some point, but at this point it's really hard to define it in like the simplified term. So we will put this as negative. And because we can't really calculate any of that for now, well, no, we can't really use pi like that. It would be irrational, and it would lie to the left of 0. And now we have, last but not least, the decimal that I was mentioning before. We know it is repeating because the sets of numbers keep repeating, as we can see. However, it is positive, and even though it is repeating, it is still a rational number. And it would lie to the right of 0 because it is positive. And those are the practice problems for classifying real numbers. All right, so I kind of want to visualize this, like visualizing the sets of numbers as subsets. let's clear this and show you what I mean. So, to kind of recap on what we've learned so far, I want to give you a graph of the types of numbers we've been using. So, counting numbers, we're using natural numbers. I'll mark that as n. So this would be natural numbers. And it's not really any different from counting or numbering things. And when it comes to whole numbers, all we're doing is adding a zero. I don't want to put this as a fraction. I almost did for some reason. But we're adding this zero to the set of natural numbers, which would make it whole numbers. And now, when we include integers, we're including numbers like going the negative numbers from like negative infinity to -3, -2, and -1. So these would be integers, and this encapsulates all of this. So hopefully you can kind of see where I'm getting with this. And then here we go with rational numbers, where we have fractions like m/n, where n is not equal to 0. This would be a rational number, which I will define as q. So kind of visualizing this, we can kind of get a grasp of how each set of number works together. The only thing that will not be a part of these subsets is when we're dealing with irrational numbers. That would be kind of on the outside. So I would kind of define it as q with a mark there. And we're thinking things like pi, for example, or the square root of 2, or any other possible number where we cannot simplify it any further. Like this is how I would visualize it. So, and I kind of want to reinforce this with even more practice problems. All right, so let us clear this. All right, so let's do this. So we want to classify each one of these into a graph of sorts. Oh, I can't doodle all of a sudden. There we go. So let's use numbers like let's make a graph first. So let's make square root of 36. Um 8/3, square root of 73. Let's do -6. And let's do a non-terminating but repeating decimal. So wait, let's change it up a bit. Instead of just zero it constantly, let's do like 3.21112111. You can kind of see where I'm going here. It's just like the threes. And now let's kind of separate this category here. Now we're going to be having the monikers like I mentioned before. Natural numbers, whole numbers, integers, rational numbers, and irrational numbers. Now, we will mark each one corresponding to which we can do. So, the square root of 36, we know if we square that, we get 6. So, how would we classify this? in the by the sets that we have. So it would be considered a natural number because it is basically a counting number. It would also be considered a whole number because it is part of the set of natural numbers. It is also considered an integer because, again, we're using the sets of natural numbers and whole numbers, which also corresponds to the integers. And it is a rational number. And that's pretty much all there is to it. Like, this is how you would classify square root of 36. Now, when it comes to 8 over 3, let's let's convert this to a decimal. It would be a repeating decimal, like 2.6 repeating. Now, I would not say this is a natural number because we do not count in decimals at all. This would also not count as a whole or an integer at all because it's not a solid whole number. However, since it is a repeating and we do have something that is simplified to the best of its abilities, it is still a rational number. Now, square root of 73. This cannot be simplified any further because you take the square root of 73, it'll probably pop up with some crazy decimal number again, trying to square the value, and we don't really get anything. So it's stuck as the square root of 73. So we can't classify it as neither of the options like a natural, whole, integer, or rational. So in this case, it is an irrational number. All right, -6. So we wouldn't really classify this as a natural or whole number because natural numbers and whole numbers do not have a negative number. However, when it comes to integers, -6 does exist. So it would be an integer. And it would also be an irrational number because it is simplified to the best of its abilities. Now, we get to the decimal, and we know it's repeating and non-terminating. However, we can't say if it will like terminate for sure because the number of ones starts to expand and increase. So we can't really simplify this any further. And in this case, since we can't really say it's repeating or anything, this would be an irrational number that we're dealing with. All right, let's clear this. And basically, I will leave that as is. Okay, let's try performing orders of operations. Let's try doing that. So, actually, no. Okay, this will be the end of the video here because I am running short on time. I hope like this is the first part of the lesson where we have accomplished this. We have so basically we have classified or we have satisfied the first objective of 1.1. So if I were to take a separate layer here. So we completed the first one. Hooray. This is complete. We do not need to worry about this. I'll continue the other parts in another video. We have been going at this for a while now. It's been not almost 40 minutes now. But hopefully you guys understand real numbers and how it works. I will upload a part 2 to this very soon. I just need more time. It'll probably be uploaded maybe tomorrow. I hope you guys have a good day, and now you know how real numbers work. Uh, the next video, we will start doing calculations with order of operations. So it'll be nice to do that. So, hope you guys have a good day. enjoy it. I hope you guys enjoy math because so far I enjoy math and I enjoy teaching. So, yeah, I say so a lot, don't I? Okay, bye. Have a good day. Good day.